In this video, I'm going to talk you through how to do a simple linear regression in Excel using the data analysis add-in. So a simple linear regression is just a straight line regression with one x and one y variable. This builds directly on correlations. I'm going to talk you through the 7 steps that we've been using in class. And so I've got made up data over here that has a woman's height in inches and then the shoe size. And again, these would be ladies' shoe sizes. So the first thing that we need to do is we need to think about what is my research question. So over here I have, does height predict shoe size? If so, what shoe size would I predict for someone who is 5'7", that is 67 inches tall? So as I figure out what's my x and y variable, it depends on that research question. So in step 1, I can just go ahead and say, well, for this step, I'm using height to predict shoe size, so my estimate for shoe size depends on how tall the person is. So shoe size is my y, because it's the dependent variable, and it depends on how tall they are. That's my x variable. So y variable is what I'm trying to predict. So I have my x and y variable figured out. Then in step 2, I've asked you to go ahead and calculate your correlation coefficient. I'm just going to go ahead and do that in Excel. I'm just going to use the correlation command. So equals CORREL. I open my parentheses, and then I give it the 2 data arrays. And in the data arrays, I do not include any text, so I don't include the labels. So I start here in A2, go down to A31, put in a comma, and then I do the same for shoe size. And it's important in Excel that I make sure I preserve the pairs. That is, this person right here who's 64 inches tall has to go with their shoe size of 9.5. It couldn't be paired with somebody else's shoe size. So that's the command I type into Excel, and that gives me a correlation coefficient of 0.725, so I'm going to call that, rounding it, 0.73. So right over here, I have my correlation coefficient. Now the next thing I ask you to do in our regression steps in class is to interpret my correlation. And when I'm interpreting it, I'm thinking about both the direction and the strength of the relationship. So if I think about the direction, I'm thinking about whether this correlation coefficient had a positive or negative sign. A positive sign meant it was a direct relationship. As x increases, y also increases. But if it was a negative sign, that would mean it's an inverse relationship. As one variable goes up, the other goes down. So I have a positive, so my direction is positive, or it's a direct relationship, and that means as height increases, shoe size tends to increase as well. And then I look at my strength, and when I think about the strength, I'm looking at the absolute value. Correlations with an absolute value closer to 1 are going to be stronger relationships than correlations with an absolute value close to 0. So I look at that and I say the absolute value in this case is 0.73. So this is a really strong positive correlation. Now, just saying really strong is still a little squishy for statistics, so let's go ahead and quantify what we mean by very strong positive correlation. So I'll look at r squared, which is the coefficient of determination. And all I do for r squared is I take my correlation coefficient and square it. So 0.725 times 0.725. So that gives me r squared. And so when I calculate that, it's 0.526. So what that tells me is the relationship between x and y can explain about 53% of the variance. Remember, correlation does not mean it's necessarily causation. So I can explain it. All right, scrolling down my next step, step 4, what I'm going to do is I'm going to actually do my regression in Excel. So I've already done it, but I'll go ahead and show you how to do that. I'll go to the data analysis add-in, click right there, and I'll go down to regression. Now I need to tell it where my y variable is. So right here you can see I've already picked a shoe size. I do include the labels now. It makes my output much nicer. And then for variable x, that's my height. I put that over there in A1 to A31. I tell it I have my labels. And then for this class, we're going to leave everything else blank and just say OK. And so that gave me my computer output. And just to make it a little prettier, we'll straighten it out a little. And so that's what I've gone ahead and pasted over here. That's my computer output. I did change how I formatted my significance of f. Remember, significance of f is my p-value. Now, that's in scientific notation because it's such a small number, but if I just right-click that and format the cell as a number, and then give it a bunch of zeros, I can see it given to me in an easier to interpret thing. So that's how I conducted the regression. And that would be step 4. So I just, again, pasted that over here. I've got my computer output. But the computer output I have to interpret to actually test my regression. So moving on with this a little more, step 5, I said to use my computer output, put this up here, to go ahead and find my p-value and test my null hypothesis. So that significance of f, right there, that's my p-value for the overall regression. That's the value I'm going to look at. I have other p-values down here, but I'm going to ignore those for now. Those aren't what I need. I just need to look at it for the general ANOVA. So that's the value I'll use to test my hypothesis for a simple linear regression. So to remind you, for any simple linear regression, my hypothesis is always going to be the null is that the slope, b1, is 0, and the alternative that it's not 0. If I put that into words, if my slope is 0, that means x does not predict y. And if it's not 0, that means x does predict y. But again, we write our hypotheses using the mathematical symbols. So I'll look at my significance value right here and compare it to my alpha level of 0.05, just like in my other hypothesis testing. And so I can see my p obtained is less than alpha of 0.05, so that means I reject the null. Since I've rejected the null, the only thing left is my alternative that x does predict y, so I'll keep going. Now remember, we've said in class, if you keep the null, it's not appropriate to go ahead and start making predictions. We would just stop. So now in step 6, I'm going to go ahead and get my slope and intercept from the computer output. So my intercept right here is conveniently labeled intercept. And then height, this is the coefficient I'm going to multiply by. This is my slope right here. Put that in blue. So there are my slope and intercept. So rounding those, I've got a value of about 0.32 for my slope and negative 12.33 for my intercept. In step 7, I ask you to go ahead and write your regression equation. So we just used the format of y equals mx plus b that we remember from linear algebra. So my slope of 0.32 times whatever value of x plus my intercept, which is negative here, so minus 12.33, that would be my regression line. That's what I would use to make predictions. To make a prediction for y, I just plug in the value of x. And that's what I ask you to do in the last step 8, where we need to make our prediction for someone who's 67 inches tall. And remember, I got that 67 inches from the problem. So all I'm going to do is plug in 67 for x here and solve for y. So that'll be 67 times 0.32 minus 12.33, which if I'm using that rounded formula is going to be 9.11. Now if I instead used exact cell references over here, I could say equals my slope in cell B18 times 67 inches plus my intercept in B17. If I do it this way, I don't have to worry about the sign of my slope or intercept. Excel will get it for me. If I do it that way, I'll get 9.15. Now, we don't round those to a whole shoe size or half shoe size. Just go ahead and your prediction is the exact value from that line. And that's just a quick refresher of how we do our 8 steps for a regression in my class.